Hi, my name is Charlotte Mason. I'm at the Cosmic Dawn Center at the University of Copenhagen. And today I want to talk to you about what we can learn about both astrophysics and cosmology from 21 centimeter observations, in particular, how we can make forecasts for this using fission matrices. So the motivation for this work is really that, as far as we can tell, dark matter seems to be cold and collisionless, but we still have no idea what dark matter actually is. And you can see this here in the matter power spectrum, where these observations are plotted against a model that we predict from cold dark matter. But there are many interesting dark matter candidates that would deviate from this cold dark matter model on small scales. So we'd like to be able to test what the matter power spectrum looks like on very small scales. And you can see here, we can do this with the Lyman alpha forest at lower redshifts. But what we would like to be able to do is to push this to smaller scales. And we think that potentially 21 centimeter observations may be a way that we can do this. So the sort of big picture goal is, how does dark matter behave on very small scales? And what I want to try and persuade you a bit about today is that we think we can answer this question by understanding when and how the first galaxies formed, and then how do they affect their surroundings, which is what we see in our 21 centimeter observations. And so this is because as the first galaxies will form in the lowest mass halos, by understanding when and how the very first galaxies formed, we think we should be able to learn something about these very low mass halos. And so really the early universe then becomes a sort of lab for testing our models of dark matter. And so in this work, we've been using the ethos effective theory of structure formation simulations, which are really a suite of simulations that include a range of different dark matter models, basically all models where dark matter is able to interact with either itself or with some kind of dark radiation. And what you're seeing are just 4 simulations from the ethos framework. And so basically in each simulation, dark matter behaves in a slightly different way. And these types of simulations will give us different predictions for the abundance of halos in the early universe. And so that's what we can see when we look at the dark matter halo mass functions. And basically different dark matter models will suppress structure formation differently, and that will imprint on the dark matter halo mass function. So there's a lot going on here, but basically each panel is a different halo mass functions with a different dark matter model, where basically models going from top to bottom. The models at the top are basically warm dark matter models, where there's very strong suppression of mass at different scales. And going towards the bottom, these models have strong dark acoustic oscillations, which would arise if dark matter can interact with a dark radiation particle, which will cause oscillations in the matter power spectrum. And you can see that show up as sort of wiggles in the halo mass function. And then from left to right, basically, we're just changing the scale at which this suppression becomes important. And so going to the far right, this mass scale moves to very, very small scales, and it effectively converges to CDM. And basically, all of these different models will then do, depending on what universe we live in, these would all do different things to affect the 21 centimeter signal. So what does that look like, for example, in the global signal? So this is a fiducial sort of example, cold dark matter global signal. But what happens if we change the dark matter model? And so what I'm going to show you now is if we now have a warm dark matter universe, which is shown here by these yellow lines, where basically the difference between the solid and the dashed is just the scale at which the suppression of halos occurs. You can see that this really can delay this 21 centimeter signal and also change its amplitude. So for example, this one to the left here, the solid line, low mass halos are really suppressed. So that delays when the first stars form, and obviously then delays the global signal. So these are just the warm dark matter models. We can also fill this in with this kind of range of different dark matter models that I was showing before from the halo mass functions. And there's a whole kind of span or range that these models can span. And some of this has been shown before by Julian. But the question is then really, can we, if we were able to observe either obviously the global signal or really the power spectrum, could we then learn which which dark matter model is preferred by our observations? So that's the goal. The problem is obviously that dark matter is not the only thing that changes the 21 centimeter signal. So there's a very large astrophysical parameter space, and you can see this here with this nice movie from 21 centimeter fast, where basically as you change these different astrophysical parameters, it will change 21 centimeter, change the 21 centimeter signal. We can see that showing up in the global signal in the power spectrum. This model here basically just contains population 2 galaxies. This has now been improved upon over the last few years, and there was a recent paper by Julian Munoz showing which included the most sort of advanced population 3 galaxy formation model. So the problem is now that there are an awful lot of parameters, both astrophysical, and then now we want to add in these dark matter model parameters. It becomes very challenging to sample this parameter space to make, if we want to make forecasts for how well we could constrain all of these parameters given our observations. So what we've done is actually take a simpler approach than doing something like an MCMC, and we've used the Fisher matrix, a Fisher matrix approach. And so this gives us a way to efficiently estimate parameter uncertainties given a fiducial model and assumed observational noise. So the way this works is that to make the assumption that our likelihood is Gaussian, we can calculate the Fisher matrix from derivatives of our model. So basically here the Fisher matrix is a function of derivatives of our model with respect to the model parameters and including the observational noise. And we can then use the Fisher matrix, we can invert the Fisher matrix to find a lower bound on the covariance matrix. So the Fisher matrix will give us lower bounds on the parameter uncertainties. So the way that we do this in practice is we pick a fiducial model and then vary one parameter at a time to calculate these derivatives, and then invert the Fisher matrix to calculate the parameter uncertainties. And the real advantage here is that it's very fast because you don't need to calculate very many simulations or very many models at all. So we found that you actually can do this with just 2 times n, where n is the number of parameters, plus 1 models. You basically just have to pick the fiducial and then 1 model either side if you want to calculate the derivatives. And so this means you can really scale this up to a very large number of parameters. But obviously we want to test that it works. So we've been testing this against results from an MCMC that was presented by Park in this paper, Park 2019. So what you're seeing here are the 2D posteriors from the MCMC in the gray contours. This is just for a CDM model with population 2 galaxies. And then our forecasted uncertainties from using the Fisher matrix technique are the orange contours. So you can see we have really good agreement with the MCMC, both in terms of the actual direction of these degeneracies between parameters, but also in the absolute scale of the uncertainties. So we think we can now sort of use this to forecast into unknown territory. And so as part of this work, we've now updated 21 centimeter fast a bit, though I think I actually haven't pushed this yet. But we have added these ethos dark matter models through a parameterization of the matter power spectrum to 21 centimeter fast. And we've also now written a Fisher matrix wrapper for 21 centimeter fast. So if you want to do these kind of quick forecasts, it may be easier to use this Fisher matrix wrapper than, for example, running a full MCMC. And that's now on GitHub and mostly documented. And so now with this fast approach, we're able to make forecasts for a larger range of parameters. So what I'm showing you here, we have now taken this most up-to-date version of the fiducial 21 centimeter simulation, the evolution of structure simulation, and made forecasts for this whole range of both population 2 and population 3 galaxy formation parameters. And what we find is that if we assume moderate foregrounds and observing with HERA for 1 year of data, observing the full power spectrum, we would be able to measure, we predict that we would be able to measure both population 2 and population 3 galaxy parameters and X-ray parameters to around and sometimes less than 10% precision. This is a nice, exciting forecast, especially that we think we'll be able to do a really good job of measuring population 3 parameters. And I think most of that comes from actually the very wide frequency range that we would be able to observe with HERA. And so you can really look back to high redshifts where those population 3 galaxies become important. We then tried to make some forecasts for the dark matter parameters too. This part is still, I would say, a bit preliminary, but based on preliminary results, it seems like we could be able to distinguish warm dark matter from cold dark matter if the warm dark matter particle had a mass of less than about 50 keV, which is quite surprising. So this part is still a bit preliminary and need to sit down and finish this off, but I think could be some pretty exciting predictions here. And so in summary, I've told you that the 21 centimeter signal contains information about early structure formation, and the timing of the structure formation really depends on the interplay between these astrophysical effects, but also on dark matter effects. And so we've included this ethos dark matter paradigm model within 21 centimeter fast and found that it changes amplitude and delays the 21 centimeter signal. And we think the upcoming 21 centimeter experiments, in particular, we forecasted experiments with HERA, could place constraints on both population 3 galaxy parameters, but also hopefully on dark matter parameters. And we've done this using this Fisher matrix wrapper for 21 centimeter fast, which you can find on GitHub. So I'm sorry that I couldn't be there live today, but I will be available on Slack to answer any questions. So thank you.